All right, good morning, Closure West. Guess what? You guys have an ops guy in your midst. I feel like I staged a little bit of a coup, as if I'm infiltrating this developer-centric conference. Here I am, an ops guy at a closure shop. I don't know any Closure. I don't even know any functional programming language. And I'm presenting at Closure West. But I guess that's more of a testament to the growing popularity of Closure and Datomic than it is to my espionage skills. My name is Vincent Rivellino. I've been the operations lead at Roomkey for the last 2 years. In fact, my 2-year work anniversary at Roomkey is going to be this Wednesday. Roomkey is a joint venture between 6 big hotel corporations: Choice, Hilton, Hyatt, IHG, Marriott, and Wyndham. The short version of Roomkey's origin is that back in the day, these hotel groups were kind of behind the curve on the whole internet booking thing, and they're stuck paying these large commissions to online travel agents. They created us to drive down their distribution costs. While it may sound like we're big and corporate, that really couldn't be further from the truth. Our technology team is small, and we operate with the speed and efficiency of a well-run startup. And we're hiring Closure devs if anybody is interested. Roomkey.com is a single-page JavaScript application whose back-end API is written in Closure. We receive roughly 10 million visitors a month, and we're totally hosted in Amazon Web Services. I will spend much of this presentation talking about AWS and CloudFormation. If some of this goes over your head, I do think I will touch on some points that go beyond AWS and that I hope you can leave with some valuable takeaways. The Closure backend is a collection of federated services, one of which includes our Datomic Deployment. This is our profile service. Today I'm going to focus on the profile service, and I'm going to talk to you about its architecture in AWS, past to present, as well as our methodologies for deployments. I'll tell you about some of the challenges we faced early on and how we leverage CloudFormation to get past them. The profile service has 2 missions. One is to provide storage and query for our user profile data. The other is to capture and query event data about the hotels our users are viewing. These are effectively 2 different applications. They could be split up into separate services. We just haven't had a need to do so yet. I'm going to take a moment and focus on the second mission, which is capturing and querying event data, as that really constitutes the lion's share of the workload of the profile service. So when you search on Roomkey.com, the search results are presented to you as an array of hotel cards. When you click on one of these cards, more detailed information about that hotel is displayed. This is what we call our hotel details page. Each time a user clicks on a hotel details page and brings up this more detailed information, an event is sent to the profile service. And when our user clicks on the book button, here in the upper right-hand corner of the hotel details page, and then here at the bottom of each of the hotel cards in the search results, events are saved in Datomic via the profile service. So what do we do with this event data? Well, one of the really simple example is that this aggregation of click event data allows us to determine which hotels might be popular, and then message the user that they really ought to consider booking that hotel. So all of the actions I just described originate in our JavaScript app, flow through our API layer, which then talk to our profile service. Here's a look at the overview of Datomic, direct from Datomic.com. Starting at the bottom right, we have the storage services, Memcache, an optional Memcache layer, to which data segments are written. The transactor, which handles writing and indexing, is on the lower left. And the 2 different implementations of peers are displayed. The one on the left is an application with an embedded peer library, and the one on the right is an example of an application without native Datomic support. And it talks to a peer REST server for reading and writing to the database. The profile service is a Ring app running on Tomcat, and it uses the embedded Datomic peer library. Our Datomic storage engine is DynamoDB. The profile service is also a write-heavy application, so we don't use Memcache as the caching layer because the benefits are really negligible for us. It's a pretty standard web application in AWS. Our peers are deployed to an auto-scaling group behind an elastic load balancer. For event capture, the peers queue up events and write them asynchronously. This allows for event capture to withstand a few minutes of transactor downtime. Our production peers can handle multiple minutes of downtime actually during peak load. We're also using Hystrix as a circuit breaker to stop sending events from our API in the case that the profile service totally croaks. The transactors are an auto-scaling group as well. And in production, we're set up for HA, which means we've got 2 running, a primary and a standby. Both the peers and transactors are running on custom AMIs that we build via our homegrown tooling. Today, this entire stack, from ELB to peers to transactors, is defined in a single CloudFormation template. Okay, before I dive into the details of our deployment, I want to review the Datomic team's instructions on how to deploy Datomic in AWS. It's pretty straightforward. They're telling us that we need to update items in configuration files and then run a few commands that they provide. Ensure transactor, ensure CF, create CF template. If we take a look at my AWS account before I ran these commands, we'll see that I have no DDB tables defined. I've got no IAM roles. I've got no S3 buckets. And I've got no EC2 security groups other than the 2 defaults and the one that I created. So after I ran these tools, we'll now see that I've got 1 DynamoDB table, and that's going to be our storage for our transactor, 2 IAM roles, 1 for the transactor, 1 for the peers, an S3 bucket for the transactor logs, and you'll see at the top there's a new security group called Datomic. And in that security group, that's where they want you to deploy your peers. So all that would be left to do to create a transactor CloudFormation stack provided by Datomic is to run the create CF stack command. That's all the way at the bottom there. So these tools make it very easy for folks who may not be super savvy with AWS to deploy Datomic rapidly. And back in the second half of 2012, when we created the profile service, we did all that. For each of our environments, staging, QA, production, we used those tools to create the AWS resources needed to run profile service and Datomic. And this was before AWS released instance profiles. So at that time, we actually had to embed the access keys that were the API credentials created for the peers by Ensure Transactor. We had to embed those in the configuration of profile service. This really wasn't fun to manage. We ended up using encrypted files in our Git repo to save and protect that configuration data. We used a few options, or we entertained a few options for deploying our transactor upgrades. The first was we could delete the entire existing stack and then create a new Datomic transactor stack using a new CloudFormation template generated by the Datomic tools. The downside of this method is that the transactor downtime would be on the order of many minutes because there's delays of tearing down the stack and then creating a new CloudFormation stack. The second, which is the one we went with, involved updating the existing stack and then manually terminating the transactors. First, we'd terminate the standby and then the primary. And after each termination, the transactor autoscaling group would replace that instance with one with an updated launch config. There are a few ways to perform, a few other ways to perform upgrades, and we'll cover those a little bit later when I get into the specifics of our current deployment. Back then, all of our back-end services were deployed on Elastic Beanstalk. So we relied on Beanstalk to deploy our peers at the time. I won't get into the nitty-gritty of Beanstalk, but I will say this about Roomkey's deployment in Amazon. Even though we moved off of it, I don't think we'd be where we are today if we hadn't used it in the first place. It's a wonderful tool that allows folks to rapidly deploy web applications to Amazon, and it has all the scalability that a small but growing company needs. So we operated like this for a while. And we use CloudFormation stack updates to handle the transactor upgrades, and we use Beanstalk to deploy our peers. And everything was working pretty good. But it started to feel a little clunky. If we needed to make configuration changes to the transactor, let's say memory settings, the object cache max, or the write and read concurrency, this required editing a properties file, which was encrypted in our Git repo, then rerunning the create.cf template tool, and that regenerated the stack template, and then we had to actually do the stack update. And at that time, we were having to take keys and security groups created by the Datomic tools and then kind of plug them into Beanstalk. So we were taking these things created by one thing and then having to move them into another. One other note there, I mean, we actually had multiple CloudFormation templates and multiple configuration files across our environments. That isn't noted in the slide. And finally, we were manually creating CloudWatch alarms around the transactor templates, or transactor metrics. So you put all these things together, and it kind of forced us to revolutionize our AWS deployment. I don't exactly remember when, but at some point along the way, we decided to ditch Elastic Beanstalk entirely and leverage CloudFormation as much as we could. In my opinion, embracing CloudFormation is akin to fully embracing AWS as an infrastructure platform. CloudFormation is a meta service that is a wrapper around every other AWS service. In a JSON formatted template, you define the AWS resources that you want to put together in a stack, and CloudFormation provisions it for you. When you're done with that stack, CloudFormation deletes all of the resources it created. And with this paradigm shift, we had to reevaluate how we created and managed our AWS resources. We asked ourselves questions like, why are we manually creating CloudWatch alarms? Why are we using a script to create IAM users and roles and their associated privileges? Why are we logging into the Beanstalk console to modify JVM heap settings? The result of this reevaluation is that we started treating many more AWS services and resources as ephemeral and throwaway. Instead, we define these things in a CloudFormation template and then let CloudFormation do the dirty work. This meant that it's okay to create resources that persist data outside of CloudFormation, such as DDB tables, S3 buckets, RDS instances. But we must define what resources can access that data and how inside of CloudFormation. The consequences of this for the profile service and our Datomic deployment meant that we had to port over what was handled either manually or via tools into a CloudFormation template. And the template created by the Datomic tools was a starting point. So the IAM roles and the instance profiles previously created by the ensure.cf tool are now defined in our CloudFormation template. The permissions to talk to DDB, S3, and the other AWS services, they're defined in the template. The firewall rules for the peers and transactors, defined in the template. And the CloudWatch alarms for the transactor metrics, they're in the template. So even though we're defining a lot in the template, there are some AWS resources we determined that must exist outside of CloudFormation. For example, the DynamoDB tables that act as Datomic storage, the Amazon machine images for transactors and peers, the S3 buckets for build artifacts, log rotation, and backups, and the SNS topics for the CloudWatch alarms. So based on our template, CloudFormation will provision all these resources for a stack and stitch them together to deploy our profile service. One of the nice things about this is that when we're done with an environment, delete a CloudFormation stack, it deletes everything that it created, and we're left with the DDB tables, the AMIs, the S3 buckets, and the SNS topics we started with. What we're really left with is our data, but no way to access it. So everything I just mentioned is a win in our book. It allowed us to make Profile Service and Datomic conform to how we evolved our AWS operations. However, here's the biggest win of them all. We ended up with a single unified CloudFormation template that can be used across all of our environments. And it sits in source control right next to the Profile Service source code. So when we tag a version of Profile Service in Git, we're not just tagging an application version, we're tagging an infrastructure version. So I won't share with you the painful details of our single unified CloudFormation template because it's 1,000 lines and 50 kilobytes large. It's actually just below the max size allowed for AWS, by AWS for a CloudFormation template. However, I will review with you the main components of that template. CloudFormation templates are split into 5 sections. Parameters, conditions, mappings, resources, and outputs. And some of these are optional. A stack's parameters are just that, data inputs consumed by CloudFormation. The stage parameter for our profile service determines for which environment that stack will be deployed. For our template, acceptable values are staging, load test, QA, and production. The location of a build artifact in S3 is passed in through a parameter. This WAR file will get passed into the peers autoscaling group, launch config. And the peers will download that WAR file before Tomcat starts, but after the instance launches. So the WAR file parameter essentially determines which version of the profile service web app that Tomcat will end up running. The SNS topics for the CloudWatch alarms, they're parameters as well. We found that managing SNS subscriptions outside of CloudFormation to be much simpler. The conditions section is a relatively new feature in CloudFormation. It allows you to set Boolean conditions based on parameter values. We're setting an isProd condition that is only true when the stage parameter is set to production. So a brief aside about conditions. Here's a quick snippet out of our CloudFormation template showing the definition of an update policy on our transactor autoscaling group. So when isProd is true, the update policy has no value. In other words, the update policy is not set for production autoscaling groups. Update policies for autoscaling groups is another CloudFormation feature that Amazon released last year. When it is set, CloudFormation will replace all running instances in an autoscaling group should that group's launch config get updated during a stack update. I wanted this feature enabled in staging, but not in production. In the mapping section of the template, we have placed our environment-specific configuration data. So for example, which DynamoDB tables to talk to, which instance types to use for the peers and transactors. And these options are looked up later on in the template based on the stage parameter. Also in the mappings are Java options and the transactor configuration, values like the memory index settings, object cache max, read and write concurrency. So they're defined directly in the template. The resources section is the bulk of the template. This is where we define what AWS resources to provision and how they relate to each other. In the resources section of the profile service template, we are defining the IAM roles and instance profiles for the peers and transactors. This is a notable difference from the template that the Datomic tools generate. This means we don't have any IAM resources hanging around that don't belong to a specific application stack. The Elastic Load Balancer and autoscaling group for the peers are included, as well as a CloudWatch alarm that triggers on the unhealthy host count Elastic Load Balancer metric. The autoscaling group feature for the transactor is defined. The configuration details in the mapping section ends up in the launch config for the transactor autoscaling group. So other CloudWatch alarms for transactor metrics include storage put back off, the generic Datomic alarm, transactor self-destruct, and memory index MB. Basically, if a transactor falls over, if it decides that it's basically a transactor crash. He asked what the transactor self-destruct alarm is. I call it a transactor suicide, because it's essentially what happens. So if we need to adjust any of the thresholds for these alarms, we're changing them in the template and not in the CloudWatch console. We actually have another autoscaling group defined for a pair host. It has a min size of 0, which is the default capacity, and a max size of 1. So there's normally nothing running. So if we need to perform administrative tasks against a Datomic database via a REPL, we'll scale this up to 1, which will bring an instance online. We'll do our thing, and then we'll scale it back down to 0. And one quick aside about our backups. So outside of the main template and in a subproject, but also in the same Git repo, is another CloudFormation template containing an auto-scaling group for a Datomic backup host. It has a min and max size of 1, so it makes sure that there's always one instance running. And the T1 micro instance that is launched just constantly runs a Datomic backup to S3 over and over. We have a tiny instance type because we don't care if it takes many hours to complete, for backups to complete. And once it completes one backup, it pauses for a moment and starts another. Okay, back to the template. The last section is the output section. And the values here are returned by the describe stacks call to the CloudFormation API, and they're also visible in the CloudFormation console. We have the names of our auto-scaling groups and the name of the peer load balancer listed as outputs. So, how do we deploy this thing now? Well, the answer to that question really depends on the environment. For our non-production stacks, we actually just perform updates of existing stacks and let CloudFormation do its thing with auto-scaling update policies defined for our peer and transactor groups. Once the stack update is kicked off, it's completely hands-off. In fact, we have our CI server, which is Jenkins, configured to auto-deploy profile service to our staging environment whenever there's changes to the source. So remember that since our CloudFormation template is in the Git repo, changes to both source and the template will trigger Jenkins builds and deploys. And the update policy feature I just mentioned, that allows for all this to happen. So let's take a look at what happens during a non-prod deploy. First off, you'll notice that our staging and QA stacks only have one peer and one transactor each. We don't need HA for these environments, so why pay for the extra instances? Okay, so let's say a deploy triggers an update for our existing CloudFormation stack, and let's assume that there's a new WAR file for the peers. Seeing an update to the peer's launch config, CloudFormation scales up the peer autoscaling group to 2. This newly launched instance will pull down the new WAR file from S3, and it starts up Tomcat. After the app comes online, its health check passes, and the ELB starts sending it traffic. CloudFormation now scales the peer group back down to 1, and the old peer is terminated. And now the peer update is complete. But let's say that same build and deploy included a new version of Datomic for the transactor. CloudFormation will go through the same process for the transactor autoscaling group. It detects, first it detects that there's an update to the transactor launch config and scales up the transactor group to 2. This new transactor will see via DDB that there's already an active Datomic transactor, so it becomes the standby transactor. After that successful launch of the new transactor, CloudFormation will scale down the group to 1, and the primary transactor is terminated. The standby transactor then detects the absence of a heartbeat from the old active, and it becomes the primary. Through the use of the auto-scaling group update policy, this whole sequence was completely handled by CloudFormation. However, we don't use that method for our production deploys. For prod deploys, we stand up an entirely new stack, manually roll over transactors to the new stack, and cut over traffic to the peers via a DNS update. Eventually, we're going to write tooling so that we can automate this new stack method and apply it to the rest of our environments. Why do we prefer it? It allows for automated testing of the new stack prior to it receiving traffic, and a DNS cutover is a lot easier and faster to roll back. Okay, so here's our production stack on the left. It's got 2 peers and HA transactors. DNS points to its load balancer. And on the right is the new production stack we just spun up. Maybe it has an update to the peers. Maybe it has an update to the transactors. And maybe both. But we're spinning up a new stack regardless. Take note, this new stack has no transactors running. And that's because the min size of the transactor autoscaling group is 0. When a new profile service stack is created, it has no transactors. We need to manually scale up the new stack's transactor group, which we'll do shortly as we scale down the transactors in the old stack. So how are those new peers doing? Well, the new peers are actually online and talking to the transactor in the old stack. There is a security group that was created outside of CloudFormation that all peers in this environment are placed in. That security group has no rules applied directly to it. Instead, the security groups for the transactors, one in each stack, allow inbound connections from that peer security group. And those rules are defined in CloudFormation. So since the peers of the new stack are fully online, we could perform sanity checks against them by hitting the new stack's load balancer directly. And if it passes, we could start sending traffic over there right now. But we're going to wait a little while to do that. For now, it's time to start moving transactors. First, we need to scale down the old transactor group and terminate the standby transactor. We do that using the AWS auto-scaling tools. Now we scale up the new transactor group. Oh, needs to go away first. Now we scale up the new transactor group to 1, and that new transactor will be our standby. Now it is time to force a failover, because right now the new peers are still talking to the old transactor. So again, we terminate the primary transactor, scale down the old transactor group to 0, and the new transactor just stepped up from being standby to active. And if all is well, we can shunt traffic over to the new peers via DNS update. Now at this time, the old peers are actually talking to the new transactor. So if there's still some residual traffic on the old stack, it's still functioning. So now we scale up the new transactor group to 2, so that we've got HA over there, and we've got our standby transactor. So after traffic is completely cut over, we're ready to nuke the old stack. So both of these deployment strategies that we implemented at Roomkey could be used by anyone running Datomic in AWS. One of my biggest goals for this presentation was to be able to share with you some concrete examples of how to deploy Datomic in Amazon Web Services. And in my GitHub account is a bare-bones web application written in Clojure that writes and queries data to a Datomic database. Unfortunately, my colleague and I had some trouble getting the Clojure side completely straightened out, but we hope to have it done in the next day or 2. But included in that project is a set of simple scripts, as well as a fully featured CloudFormation template, which is complete, that allows you to deploy it to AWS without using any of the tools provided by Datomic. It does require a Datomic Pro or a Pro Starter license, as well as an AWS account that will be charged if you deploy it. That said, if you're interested in seeing a reference implementation of Datomic in AWS, by all means, check it out. And everything I talked about just now, IAM policy, auto-scaling groups, update policy, elastic load balancing, security group ingress rules, conditions, all of those things are included in the template in that project. The included update stack shell script will kick off an automated deploy, just like we performed on our non-production stacks. I also want to mention that while we stopped relying on the tools provided by the Datomic team, that doesn't mean that we disapprove of them or think poorly of those tools. It's simply that we outgrew them. And when we outgrew them, we took real ownership of our Datomic deployment. So, and also, if some of the topics specific to Amazon Web Services weren't necessarily your cup of tea, I do hope you walk away with one conclusion. That is to embrace your platform. Whether you're in Amazon or on SoftLayer, in Google Cloud or on premises, the only way to successfully launch and deploy any application is to embrace the platform on which it runs. And that goes for both development and operations. While this talk had an operational focus, the untold story is that the collaboration that myself, as well as our other ops guy, enjoy with our development group back in Virginia. I could not have built such a full-featured CloudFormation template for our profile service without their insight and without their willingness to adapt the application to our platform. So I say again, embrace your platform. So if anybody has any questions, I'd be happy to field them right now.